Hello, today we will be using physics to determine how the speed of a pendulum's oscillation is affected by two different factors, that being the weight at the end of the pendulum and the length of the pendulum itself. We will do this by using this formula, which takes 2 pi and times it by the square root of the length of the pendulum divided by 9.8, which is the constant g that represents the acceleration of a free-falling object. For our experiment, we will take two pendulums, one longer than the other, and take the lightest of two weights and attach them to the first pendulum and hook it in a stable position. We will then set off the pendulum and record its simple harmonic motion for 10 oscillations, and then divide it by 10, thus gaining the period for the pendulum. This experiment will be repeated 3 times with each pendulum, and the average of 3 experiments will be recorded. Then we will repeat the experiment with a heavier weight in order to show that there is no effect/change on the system based on weight. We will then perform the calculations for each pendulum, and we will compare it to our experiment. When completed, we will construct a table that will illustrate that the weight had no effect on the period and the formula was accurately calculated to the period based on the data gathered from the previous steps.
Hello everyone, this is Colton of Group 1, and today I'm going to be discussing the physics behind our experiment, which is that two pendulums of different mass, in this example I'm using 3 kilograms for A and 5 kilograms for B, with the same string length, when released at the same time from the same position, will move in the same way, the same speed, at the same time, at each and every same position. So the main part of this is going to be gravity. Now, despite them being different masses, and despite B requiring more force to move its mass, the constant of gravity is 9.8 meters per second squared in terms of acceleration. So what that means is, despite B having more force acted upon it, it will move at the same rate of acceleration, the same rate of change for velocity as mass A.
Here you can see our calculations using the formula for both the 2-foot and the 4-foot pendulum. We convert the feet to meters and then plug it into the equation to find that the 4-foot rope will have a period of 2.28 seconds and the 2-foot rope will have a period of 1.50 seconds. Here we have the short rope small weight experiments. The rope in this experiment was 2 feet and the weight was 1 pound. Each of the periods present in each experiment is labeled on the screen. Now here we have the short rope large weight experiments. In this experiment, the rope is still 2 feet and the weight is now 10 pounds. Each of the periods is still labeled on the screen for each experiment. Now, here we have the long rope, small weight experiments. In these experiments, the rope is 4 feet and the weight is 1 pound. Yet again, each period is labeled on the screen for each of the experiments performed. Lastly, here we have the long rope large weight experiments. In these experiments, the rope is 4 feet and the weight is 10 pounds. Yet again, each period is labeled on the screen for each experiment performed. As can be seen in this table, the periods calculated with our formula are very close to the actual periods found throughout our experiments. Furthermore, the periods of the ropes with different weights on them are also very close. This shows us 2 things. Firstly, that the formula can be used to accurately calculate the period of a pendulum, and secondly, that the weight at the end of a pendulum does not affect the period of the pendulum's oscillation.